Welcome, everyone. We are now starting our next talk. So at the end of the next talk, there will be a Q&A session. So if you have a question, please come downstairs here so that I can take your questions and enjoy the talk.
Thank you for the opportunity to speak. My name is Jim Colliander, and I'm a professor at the University of British Columbia and one of the folks that are with the International Interactive Computing Collaboration, or 2I2C. Today, I'm serving as a stand-in for my collaborator, Dr. Tasha Snow, who could not come to Paris. And I'm going to be talking about some work that 2I2C has been doing with Tasha and a group of Cryosphere researchers that are associated with the NASA ICESat-2 mission. There's a link right here, bit.ly/CryoCloud-JupyterCon, that contains a path that when clicked will bring you to my slides. So if you want to follow some of the hyperlinks or have access to my slides, you can grab that link. And I'll try to remember to show that link at the end of my talk as well. So this is a project that involves a lot of collaborators, and it emerged with some initial conversations leading to 2 NASA-funded grants with Tasha Snow, Fernando Perez, Matthew Siegfried, and myself, and it's now advancing forward. As a sort of high-level summary, I want to describe a social plus technology experiment that is underway right now that involves the use of JupyterHub adjacent to a data lake and interactions with scientists through hackathons, conferences, and so forth as we try to iterate and improve open science workflows to understand the cryosphere. An outline of my talk. In the first part, I'm going to make some remarks that overlap in some sense with some of the things that Fernando discussed yesterday about open science, and then I'll tell you about CryoCloud and this social plus technology experiment. And then I'd like to make the argument that Jupyter has the potential to play a significant role in combating the climate crisis by recognizing CryoCloud as a motif of a general pattern that can allow us to understand the Earth system better. So first on open science. What is science? We all kind of take it for granted, but it's not the production of PDFs. That's not the objective function for science. It may be perceived by that as that by some of us, but it's not. It's a systematic social enterprise that humans engage in to try to understand the world with testable explanations and predictions. And the central activity, which overlaps with Paul Romer's talk just a moment ago with the drawing that he made, the central activity is the exchange of information. And Jupyter and the tools that this community has built and are building are changing the way that we can exchange information between humans. And so I think we are contributing to the underlying infrastructure that allows science to unfold. There are 2 emerging global processes that I think are really exciting right now. Ideas from statistics, mathematics, and computing are changing knowledge areas and industry sectors. Take adjectives like digital, precision, smart, computational, and put them in front of nouns like agriculture, humanities, cancer, and you have whole new fields. And there's also a big change in the way that we work together, accelerated by the pandemic, that technology is changing the way that we work through Jupyter or Zoom or cloud computing, real-time collaboration. And I think that we can use these processes and influence them with open source ideas to make science more open and also to manage the Earth in better ways. There is a giant problem that seems a little strange. Science is underperforming. It's maybe never performed better than it is right now, but it's not performing at the level that it could. We have misrepresentation. We have certain groups of people that are excluded. We have problems in exchanging information. We have paywalls. So this lack of high performance at science may not seem like such a big problem because really we are producing science right now better than we were last year, but it's a bleeding head wound given the problems that we face as a globe. So we have to find ways to make science perform up to potential. And the way that we do that is by eliminating barriers to participation, eliminating barriers to collaboration, eliminating barriers to sharing of knowledge. An example took place at that meeting 11 months ago where Fernando Perez and I were in Vail meeting with heliophysicists. And this student that you see in the foreground and his thesis supervisor you see in the background were there. So Greg Cook, a student, was studying exoplanet atmospheres. And the way that he was doing so involved, let's say, multiple hours to study one planet around one star. And I knew a little bit about the exoplanet archive that's available through an API from NASA. And we had set up a JupyterHub for this, this event. And after showing Greg a little bit how to use an API to pull in information on the exoplanets, in that afternoon, he recognized a 2-order of magnitude improvement in his capacity to carry out data-intensive research. So instead of planning his thesis around a careful study of one exoplanet around one star, he began to imagine doing comparative studies around all of the exoplanets. And this transformation that took place very quickly, because information can be shared so much more effectively, and collaboration took place at this hackathon, I think is a nice little anecdote that captures a lot of what the potential of open science enabled by the technology that we are building in this room does for all of science. There's also a top-down movement right now to make these changes that I'm hinting at systematic. So there's a recommendation from UNESCO. Countries all across the globe are rallying behind this transformation in the way that we do science. And I've had the privilege and opportunity to work with some of the folks at NASA that are pushing forward this initiative called TOPS and the Open Source Science Initiative. Fernando referenced yesterday, and I want to highlight today, that leadership by NASA led to a US agency-wide recognition in January of 2023 as the Year of Open Science, and all federal agencies in the United States are rallying behind this new way to think about the scientific enterprise. That means that we have an inflection point. We have an opportunity to lean into the changes in the way we communicate, the changes in format that we heard about in terms of scholarly communication just a few moments ago, and really influence the way that science unfolds over the coming decade. So this 2023 Year of Open Science, the TOPS initiative is being led by Dr. Kjell Genteman, and you can see at the bottom these agencies that have endorsed this 2023 year. So with some folks that are familiar in this community and under leadership by Dr. Genteman, we had a paper called Science Storms the Cloud that explains in some ways how science will transform or is in the process of transforming due to the presence of cloud technologies and technology facilitated by the Jupyter ecosystem. So what are the values that we should think of as really guiding science in the next century? I think a guiding value is a concept of intellectual generosity. We should share ideas respectfully, and we should learn from each other. And there's a link there that looks into a mathematician named William Thurston's viewpoint on mathematics. And this philosopher, Morris, develops the idea, the virtue of intellectual generosity by studying what Professor Thurston said about his views on mathematics. Another value that I think guides this new era of open science is intellectual humility. So this viral image that was created by Matt Might shows the path towards a PhD. So this giant circle is all knowledge. And you start to learn a little bit in grad school or in undergrad, and then finally you start tunneling towards the edge of knowledge, and then finally you make just the tiniest breakthrough outside of the boundary of knowledge, and that's your PhD. And you should be very proud if you pull that off. But I think it's really important that we also recognize that we are building on top of a massive background of knowledge, expertise, that we are really, standing on the shoulders of giants, so to speak, and recognizing that the thoughts and advances and breakthroughs that we make are really a product of prior work by others. And recognizing that all the time, I think makes us interact in a different way, and it's kind of the value which, when embedded, helps us be more open in our science. And then a last bit on the values of open science are these axioms by Ardila that I've transformed slightly. Ardila posed these about students and mathematics, and I've rewritten them about science. So what these say, essentially, is that scientific talent is distributed uniformly across human population. It is not distributed in any way that's based on race or based on where you happen to have been born or your gender. Everyone has the same uniform distribution of talent potential. But we don't have systems that respect this type of axioms on talent. And we don't have systems that enable everyone to participate equally in the scientific enterprise. And when you see these axioms in front of you, I think they're implicit in many of the things that we imagine about humans. But when you really look at them and you think, well, yeah, science is awesome, and everyone should have a right to participate in it, but you don't really write down these axioms and reflect on what it means about your privilege, the way that you managed to maybe make it through Les Grandes Écoles or make it into an Ivy League school and get all these opportunities. But there are other people that don't have that path. And looking at these axioms helps me to really think about the potential for an open science future involving more people participating in the scientific enterprise. So with these grand and values-based ideas, we've started an experiment to try to explore some ways that technology and social innovation might advance towards these large goals of open science, and that's CryoCloud. So CryoCloud is a social plus technology experiment that involves the deployment of a persistent JupyterHub adjacent to ICET2 data in US West 2 AWS, and it's also adjacent to lots of other open data that NASA has made available for researchers. And then there's a sequence of workshops that the Cryosphere research community, so Cryosphere is the Earth's ice. These are the people that study alpine glaciers and continental ice shelves. And we heard a talk yesterday by Luis Lopez on some aspects of this research area. And we want to use these workshops and conferences to engage with the researchers that are using the technology to collaborate in new ways, to iteratively improve the use of the technology and to iteratively improve the social structures around these conferences and workshops, and indeed across this whole community of researchers, to try to achieve these benefits of open science, accelerating discovery, improving participation, making young researchers, bringing them up to speed more quickly. And so this build, measure, learn loop is a process for us to get feedback through the experience of learning at workshops and conferences and test whether or not we're really moving forward on these objectives of open science. So this is a timeline of some recent and future upcoming workshops. So back in 2022 in the summer, 2I2C operated a JupyterHub for a short period of time for a hack week called SnowX Hack Week. And we left that hub up for a little bit longer than the week-long hack week that took place in summer of 2022, but we had to wind it down because of costs. And some of the feedback from the participants in the SnowX Hack Week were, hey, we really like this thing, but we wish that it were available persistently because we have to keep using it. But we had to wind it down. And that conversation eventually led to the launch of the CryoCloud Hub, which will indeed run for 2 more years outside of this chart. And then there's a sequence of events, one looking at the Greenland ice sheet, another looking at the Western Antarctic ice sheet. And we aim to have a culminating event at AGU in 2023. And that AGU event, we hope, will be sort of like Paris 1887, where it will be a showcase example of what a future of open science will look like because of what we have learned through this iterative process of using the hub through these workshops. In May of 2022, the ICET2 science team met and had some comments about the cloud that did not resonate with some of the scientists that have launched CryoCloud, suggesting that the time to transition to cloud will be difficult. It's not obviously more collaborative. It might be really difficult. It's going to be costly. And that didn't ring true. So part of our experiment is to confront this cloudy hesitation. And we've done so using JupyterHub, led by the engineers at 2I2C, a new organization, a not-for-profit, that delivers interactive computing infrastructure with a right to replicate. And we have a model that allows us to interact through the communities, the engineering folks, and the scientists. And we have some structure that is quite familiar to people in the Jupyter ecosystem, where we are relying on commercial cloud infrastructure, the very flexible JupyterHub for delivering interfaces for interacting with that data through an authentication layer, and some support services. So we have done some surveys of recent interactions with this community. So on these 2 pie charts are answers to the following question. What % of your computing will be conducted in the cloud today? And what % of your research computing do you expect will be conducted in the cloud 5 years from now? So 0% of this blue area here is 0% today. They're not using the cloud at all. But 5 years from now, they're expecting that little tiny thin pie slice will be the people that don't plan to use the cloud. So the community, I think their respondents here were 61 people. They are anticipating a transition to cloudy workflows. We also asked questions about whether or not they intend to change language in order to take advantage of the cloud. And you see that almost half of the folks that were surveyed intend to change their coding language in order to use the cloud. So significant switches in behavior are anticipated. So CryoCloud is an example of a community focused on glaciers using data and trying to understand the melt of glaciers caused by climate change and caused by seasonal variation. But it's a bit of a motif. There are several communities that have this kind of academic research community pattern. The Cryosphere folks have formed CryoCloud. There's another group that 2I2C is serving called M² Lines that's focused on climate models. Another group is focused on volcanology. Another group is focused on oceans. These communities are by and large trying to produce academic research and understand and monitor different aspects of the Earth system, and they're not very well integrated. They're not so connected. But you can imagine that dynamics like El Niño and La Niña generate atmospheric rivers that cause snow to accumulate on top of volcanoes, and that snow in turn forms glaciers. Then those glaciers melt and flow down into the rivers. And so the Earth system is very well connected, but we haven't yet really integrated all of this Earth system activity as well as I think we can. And implicit in there is, I think, a bit of a call to action for the Jupyter community that I'll come to in a moment. We also have another pattern of communities that we're serving, which I think of as multi-stakeholder research to operations communities. It's not just academic researchers, but it's folks like Wi-Fire that are trying to understand all aspects of wildfire, not just research models and ML models that forecast how wildfire might unfold, but how will we mobilize emergency response, and what type of preventive action should we take to protect communities against wildfire. Another large community is trying to manage the North American water resource called Cairo, and this also involves policymakers, hydrological researchers, first responders, people looking after hydrological power systems, and so forth. And an emerging program led by NASA with Office of Management and Budget input is going to look at managing greenhouse gases. But you might also consider future communities that are looking after biodiversity versus time, and maybe also communities that are looking after economic indicators localized in space, kind of following the work of Nobel laureate Nordhaus, and looking at how is economy associated with carbon and things like this. These communities can be thought of as digital villages that grow up adjacent to a digital watering hole or a data lake. And these communities are served by interoperable open source technology using the Jupyter ecosystem and ideas that I think come out of open source on how to engage socially and work collaboratively. And the leadership from Jupyter, I think, is setting the stage for these types of communities to work better together technologically and socially. And so I think we together are helping to enable an integration of open source earth science teams that can create a new cohort, a new future generation that understands the Earth better and may be able to monitor it and manage it and hopefully mitigate the crisis that we face. I'm not sure if this audio will come through. The video is not available, I must be off the net. But what I wanted to show there was President Macron's brief speech to the United States Congress, wherein he asserts that there is no planet B. And there isn't. We're not going to Mars to solve the climate crisis. We have to figure out a way to do it here. Thank you for the opportunity to address you today. It's a great honor to be here at JupyterCon. I look forward to having any questions that you might have.
Any questions?
So this is a very general aspect, but I think a very important one, and I'd really like to hear your thoughts on it. So I am from economic geography, so I am connected to both geographers and economists. And from my experience, there's still this barrier in both areas that some people really struggle with programming. It was really the case also for me personally that I started to get involved into programming because it is open source, and I think this is very important for a lot of reasons, because commercial systems are basically good at locking people in. But I have been wondered a lot, because I completely agree that we have to make science more inclusive, how you think we could address such barriers where people sort of have it in their head that they're not smart enough to do mathematics, or that they're not smart enough to do programming.
So there were a few, the question was, how can we make, there was less of a question there, more of a statement, so I'm trying to translate some of what you said into a question. So how can we ensure that the systems that we use for science aren't owned by a company? That was one part that I heard in what you were saying. And how can we make it more accessible so that barriers associated with mathematical skill or coding skill are not preventing people from other discipline areas to enter? Is that a fair translation of your two questions? Okay, great. So on the first one, I think that 2I2C has introduced something that is novel to open source, that is addressing your first question about avoiding vendor lock-in. So we've pioneered this idea of a right to replicate. And in so doing, we promise to the partners that use our infrastructure that they will have access to the infrastructure as code as open source. And moreover, the infrastructure as code will be written in such a way that it can be interoperably redeployed across different commercial cloud vendors. So in this way, if a university or a research team is using infrastructure from 2I2C on Google, and for some reason they decide they don't want to use Google, they want to switch, then our infrastructure is designed to allow them to switch to Amazon. And if a few months from now or years from now, they decide that they don't want to rely upon 2I2C's engineering team to operate this infrastructure for them, then we will facilitate their movement of the management of the infrastructure they are using from 2I2C's engineering team to their own engineering team. We do this purposefully because we believe that the talent necessary to run the infrastructure for collaboration, the stack for science, needs to be owned by no one. It needs to be a digital public good, similar to the alphabet. Everyone should have access to this technology. And I think the right to replicate is a mobilization that goes beyond open source and achieves the outcome of making the commercial cloud into an interoperable utility and avoids vendor lock-in. On your second question, I'm a math professor. I strongly believe that everyone can understand mathematics, coding, and statistics a lot better than we do right now. But I also think that we have significant challenges in pedagogy and arrogance and kind of academic royalty. But mathematics is the infrastructure for thinking well. It's the underlying logic for how to understand nature. Mathematicians are the lawyers of the universe. We understand how the universe works legally through all of the rules. And I strongly believe that everyone needs to understand it and can understand it. But making that happen is difficult. But I think the ideas around open science, that intellectual generosity and humility, is also partly the way that we can take some of the arrogance out of the way, get rid of some of that, and let people actually learn. There is a transformation, a sort of mathematization of pretty much all disciplines and industry sectors like I was suggesting. But we have to accelerate that in a more respectful and open way.
Thank you very much. Are there any more questions?
There's one over here on the right.
Thank you so much for the presentation. It's very enlightening. I was wondering, you talk about all these opportunities of collaboration and open science and stuff. This is great. Do you think it will allow the people that take decisions, like the governments, to take better decisions based on this? Since we already have so much information and data to show climate change, does this acceleration will improve the vision of science?
So the optimist in me says, I hope so, but let me also reflect on that slightly. So the work on CMIP and the intergovernmental panels on climate change right now are a source of pessimism for me. So the peer-reviewed work on climate change has just gotten more and more precise, and the predictions have gotten more and more dire. But I think we in the academic world find that to be a persuasive case. Look, it's peer-reviewed, you know. We've got so many significant digits here, we've nailed it down. And we expect that that kind of heft, that academic shininess, is going to persuade governments to change direction. But so far, you know, notwithstanding some nice signals, it hasn't. And so I'm optimistic that if we can get people engaged in the data, engaged in the monitoring, we can, instead of thinking about, you know, a UN-level global conversation in places like Paris leading to the Paris Agreement, if we can have children looking at the impact of climate change informed by data with satellites looking at their community, then potentially the mobilization and opening of science will change the way citizens understand, not just through peer review and authoritative persuasion from elite scientists, but instead they can see it, measure it, and participate in the process of discovery and mitigation. Then I think we can maybe mobilize and change things. But that's a big call, but that's kind of why, that's my jam. I want these data tools and these social transformations to change the world for the better.
Thank you very much. Unfortunately, our time is up, so if there are any more questions, please reach out to the speaker directly. Thank you.